Hello. So in today's video, we'll discuss the Walrasian demand correspondence or function. Okay. So in the last episode, we said that now we are going to focus on our attention on some properties of basically two things. Okay, in the utility maximization problem. So the first is that the consumer's set of optimal consumption bundles. So that would be the solution set of the utility maximization problem, right? And the other important aspect would be the consumer's maximal utility value, right? So that would be the value function of the UMP problem. So that would be something later. But today we'll discuss on the first point. Okay, so that would be the optimal consumption bundles. So that would be the solution set of that problem. Okay, so instead of solving this problem, so it is more important to discuss the properties that the solution needs to satisfy, right? So, and we're going to introduce this idea called Walrasian demand correspondence or Walrasian demand function. Okay, so that would be some solution set for this UMP problem, okay, utility maximization problem. So essentially, okay, so what is this Walrasian demand? So the rule that assigns the set of optimal consumption vectors, remember we have L dimensions, right? So there will be a vector in the utility maximization problem to each price wealth situation. So that would be P and W, right? So that's which is strictly greater than zero in each dimension, right? And that would be denoted by this this demand function or this demand correspondence. Okay. So let's write this note down. Okay, so we use X, okay, and given some price and given some wealth, okay, so this X will be a real vector with positive real values in L dimensions. Okay, and this is the optimal consumption vectors in the UMP. Okay, and under each situation with this price and wealth combination. Okay, and each dimension is strictly greater than zero. Okay, and this is, so this X is called Walrasian, or sometimes we call it ordinary or just market demand. Okay. And importantly, this is a correspondence. Okay. We do not directly say that this is a function. Okay. So function would be just a special case of correspondence. So if we have a more general correspondence, then the output could be, we could map from one value of input to multiple values of output to be a set, right? So essentially we can, if the indifference curve is we have that, if that is convex everywhere, and the tangent point to the budget constraint will be just a point. Okay, but if we have some, let's draw this picture. Okay, so the reason why we're having this correspondence is that if, okay, so this would be x1 and x2. Okay, and this is the budget. Okay, with this straight line. So if we have this preference or this indifference set, this curve to be convex everywhere, okay, and then we only have this tangent point to be the solution, okay, and in this case we can call this as a function, okay, so x will be just a point. But however, okay, it will be also possible if this was the budget, okay, so let's change the color and you maybe use blue. So let's say if this indifference curve or indifference set, it has some part straight and tangent to it to this perfectly coincide with this budget. Okay, so let's say it looks like this. Okay. It goes here and then like this. Okay, so if this is the case, then we will have this a lot of infinitely many of those points, and this forms up a set, right? So this set is called a correspondence. Okay, so all those points, they consist of this X set. Okay, all right, so that's essentially the idea why we're introducing this as a correspondence. And you might recall this concept from the existence of Nash equilibrium, right? So in the game theory series, okay. So if that if we squeeze this to one single point and that is tangent to the budget, then we only have one point as a solution, and we can call this as a function. Okay, but in general, this would be a correspondence on the right. Okay, good. So let it be this Walrasian domain correspondence or function. Okay. All right. And if this x is single valued, okay, if there's only one value in the set, and then we can call this as a function. Okay. So if x has one value, then we call it as Walrasian or ordinary or market demand function. Okay. So this would be a special case to a correspondence. Good. So next, we'll discuss some properties. Okay, and that is satisfied by the Walrasian demand as the solution to this problem. Okay, so this would be the proposition 3.d.2. Okay, and you can see that in the analysis of economic theory, and it is very important to understand the mechanism or the properties of either the problem itself or the solutions, instead of directly solving the problems, right? So rather than just solving the problems, and it is also very useful and meaningful to understand the question itself or the problem itself, right? To characterize those properties. Okay, and that is essentially the importance of some analysis in economics, right? To explain things. Okay, so now, good. So now let's suppose that this utility function is a continuous function. Okay. And it satisfies the local non-satiation. Local non-satiated preference relation defined X, which is R plus L. Okay, so it is also important to notice that sometimes we can, if you can recall those properties for the preference relation, including the continuous or convex or local non-satiation or monotone. So those properties, the reason that we spend a lot of time to discuss those properties is that for example in describing those solutions, right, we might need those important properties from the preference relations, right? So that's the reason that we take a lot of time to prepare those properties that look might complicated, but here actually those are very useful to derive some also equally important properties in those solutions in the utility maximization problems, right? So those are very useful properties in the preference relations. Okay, so that's something else. Let's continue on this proposition. So suppose the utility is continuous utility function, okay, representing a local non-satiated preference relation defined on X, which is L-dimensional positive root numbers, which are vector. Okay. So then, okay, then the Walrasian demand correspondence X PW, it has the following properties. Okay, so we're going to introduce 3 properties for that. Okay, so the first is called homogeneity. Of degree 0 in this price and wealth. Okay, so it means that is our solution X, if we factor this by alpha to both price and wealth, and then this is still the same X as before. Okay, for any P W and some number alpha. Okay. All right. So the first one looks not difficult, right? So the second one is called Walrasian law. Okay. So it's saying that if we inner product P and X, and this has to be W. So this inequality, it is binding. Okay. So the budget constraint is binding. So it means that we have to spend all the money we have for all, okay, for all X. Okay, good. So the last property is that is the convexity or the uniqueness for this X. Okay. So it's saying that if this preference relation is convex, so the upper contour set is convex, so that this utility function, and remember that this utility function has to be quasi-concave, right? Okay. Then this solution X is a convex set. Okay, so here, pay attention to this convex set. So it is, it's not a convex function. Okay, so convex set, you have to consider this as a set rather than a function on reals. Okay, so moreover, if this preference relation is strictly convex, okay, so we cannot have any boundaries. Okay, so it's strictly convex, so that this g function is strictly quasi-concave, then the solution x pw, it only has one single element or one single value. Okay, so it becomes a function rather than a correspondence. Okay, good. So now let's start to prove those properties. Okay, so for the first, so this would be very easy. So for the homogeneity, so for any scalar alpha, okay, to be positive, so we simply multiply. Okay, so we're in the set of x. If we multiply p by alpha, inner product with x, and also multiply w by alpha, and we can simply cancel the alpha on both sides, and it becomes exactly the same as before. Okay. Okay. And so that means the set of visible consumption bundles in the UMP, it doesn't change when all prices and wealth are multiplied simultaneously by some positive number alpha. Okay, so then the UMP bundle, or this X, the solution has to be the same in the two different cases. Okay, so XP W, it has to be the same as X alpha P alpha W. Okay, so this doesn't need any requirements or any assumptions on this utility function. Good. So that's the homogeneity of degree 0 on X. And then next we're going to show the Walrasian law. Okay, so it is derived from the local non-satiation. Okay, so local non-satiation is, essentially, remember that the meaning of local non-satiation is a weaker property than the strong monotone and monotonicity, right? So local non-satiation means that if we have some X as element of consumption set big X, then within a very small range, epsilon positive number, a range of epsilon around this X, we can always find this some other point, okay, which is more preferred than this X itself. Okay, so that would be the meaning of local non-satiation, and intuitively, and it is also straightforward, right? Because we on the space, for example, with positive real numbers with x1 and x2 on this space of X, then we could always find such point which is close to some original point X, and that new point is preferred than X itself, right? Okay, so and that is the local non-satiation, right? Good. So now we're gonna use this to derive the Walrasian law. So Walrasian law is essentially saying that the consumption bundle P inner product with X, it has to be exactly equal to W. So this inequality has to be binding. Okay. So how do you do that? So if P inner product X, okay, so if, let's suppose if this is less than W for some X, okay, then there must be another, as we said, there'll be another point close to this, but that is better than this, right? Another bundle y sufficiently close to x, but it's also satisfying that p inner product y is still this is still satisfying the budget constraint. Okay, and also we find that this y is strictly preferred to x. Okay, and then we can immediately observe that this will contradict x being the optimal in the UMP, right? Because y in this case it will be better, or it will be more optimal than x, so x becomes suboptimal. Right? So this would contradict x being optimal in this utility maximization problem, since y is optimal now, and x is not. Okay, so this is just a note in the bracket. Okay, good. So it maybe is more optimal, right? Maybe there is some other optimal, but it doesn't matter, right? Okay, maybe we should erase this so we know the idea, right? So this would be a little bit confusing, but we know that, okay, now x it is worse than y, right? So but y is still satisfying the budget constraint, so why not we just choose y, right? Okay, so here x is not optimal, and it is contradictory to the starting point, right? To contradictory to this. So when we're seeing that x is an element in the x set, then this x has to be optimal, right? Okay, so graphically, okay, so this is important to have some figures. So let's say this x1, x2, okay. So this is where the budget constraint, okay. So, and we want to have some y strictly better than x. Okay, let's say if this x, okay, because we're saying that we're supposing that px, p inner product x is less than w, so this x has to be below this budget line, right? So let's suppose this x is somewhere here. Okay, so we can always find some small positive real number epsilon to make a circle or make a ball with the center of this x, and then this would be radius of epsilon. Okay, then we could find some point y. Okay, let's say this is point y, such that this y is still within the budget set. So p inner product y is still less than w, and but importantly, this y by the local non-association, right? So this x, we can always find such y, right, to be strictly better or strictly preferred to x itself. Okay, good. So this means that we have to spend all the money that we can, right? So when we spend all the money, then this x has to be on this budget line itself. Okay. Good. So that would be the second property. Okay. And let's move on for the third. So in the third one, we're trying to prove that this set x pw it is convex, okay, or it's unique. Okay. All right. Good. So here the very important point is that this convexity, okay, we're talking about the convexity for some set, okay, it's not for any function, Okay, so that is something very important to keep in mind. So when we're saying that some set is convex, so mathematically, if we have 2 points, okay, in the set, and we have the convex combination of those 2 points, and this combination, it has to still to be in the set itself. Okay, good. So that's the convexity for the set. And okay, so now let's start to prove this. So suppose this is just a note. Okay. Okay, so suppose that this utility function is quasi-concave, so the upper contour side is convex, okay, and that there are two bundles, x and x prime, and x and x prime, they're not the same, okay, but both are elements of the solution set. Okay. So to prove this result, we're going to show that some convex combination of x and x prime. Okay. So we show that this is an element of the solution set X for any of. Okay. All right. So to begin with, we know that so we know that the because those two x and x prime, they're in the solution set X, so we have those two in with the same utility level, right? So, which are the optimal level of utilities, right? So then we denote this by U star. Okay, so by the quasi-concavity, this U x double prime, it has to be greater than or equal to U star. Okay, and in addition, since P inner product X, this is less than or equal to W, and the same for X prime, we also have P inner product X double prime, which is P inner product alpha X plus 1 minus alpha X prime, and this has to be less than or equal to W, right? So this also satisfies the budget constraint. Okay, so this now we have this X double prime, it is satisfying this budget constraint, and at the same time, the utility of X double prime, it is not less than U star. So therefore, this X double prime, it is a feasible choice in the UMP. Okay. So to make it simple, So x double prime, it is feasible because this this budget set BPW, it is a convex set. Okay. So since u x double prime, this is greater than or equal to u star, and this is feasible, then this x double prime, it has to be also a solution. Okay. So now what we have shown is that, okay, so x and x single prime, they're in the solution set X, and their convex combination is also in the set. So now we have proved that this set X, it is a convex set. Okay. Given that the utility is quasi-concave, or that the preference relation is convex. Okay. All right. So now let's prove the second half of the third property. Okay, so suppose this U, now it is strictly quasi-concave, or this preference relation, it is strictly convex. Okay, so using the very similar argument that we did just right now, but instead now we're using the strict quasi-concavity, then we could easily establish that the x double prime, it is also a feasible choice, and that this utility of x double prime is greater than the some optimal value of u star for all the alpha. Okay. And because, okay, now we should write this down. Okay. So using similar arguments, but with strict quasi-concavity, then we can show that x double prime is a feasible choice, and the utility of x double prime is strictly greater than u star for all alpha. Okay, this has to be open set, right? We're using the strict convexity here. Okay, so, and because this will contradict to the assumption that x and x single prime, they are both elements of X set. Okay. So this is a proof, another proof by contradiction, right? So because this contradicts the assumption that X and X single prime, they're elements of X, PW, so we can conclude that there can be at most one element in the set X. Okay, so there'll be a single value set X. Okay, so now let's try to show this on a picture. We might have already showed this, right? Maybe in the beginning. Okay, so this will be exactly almost the same picture as this. Okay, so now let's just draw this again. So for the convexity, which is not strict convexity of the preference, okay. So if let's say this is the budget, okay, so this x1, x2, this is the budget. Let's change the color, and let's say if this preference is convex, but it is not strictly convex, so we might have some part, okay, to be straight, and okay, and it has some part coincide with the budget itself. And let's suppose this x, that in our argument x is here, x prime is somewhere here, and the convex combination double prime is here. Okay, so this would be the set with this utility level u star. Okay, so this is a case of convexity, but not strict convexity of the preferences. Okay, or in other words, this is the just the quasi-concavity for the utility. Okay, so in this case, it implies the convexity of this x. Okay, so it means that, so what do we mean by this convexity of x? So again, remember in the first picture, we have already labeled that this will be the set of x, right? From those two endpoints, and this is a set of for this x for those x values. Okay. Convexity of preferences implies convexity of set x. Okay, so here, as we just mentioned or addressed, a very important point is that this set x, now we're talking about the convexity of some set x. Okay, so this is not convexity of function or some function of or any function. We're not talking about any function here. Okay, we're talking about the convexity of set x. So here the set x is just as we just labeled by this big curly bracket, by this x pw on the picture. Okay, so again, so mathematically, given by the convexity, we mean that for any convex combination, this point x double prime is still within the set. Okay, good. So how about the other case? Okay, so put this also on the figure. It is saying that so the strict convexity of the preferences or strict quasi-concavity of the utility, so those are essentially the same thing. Okay, so they imply that this x, it only has a single value. Okay, so let's suppose the budget is something like this. Okay, and let's say this indifference curve would be something strictly convex. Okay, this set of the preference is strictly convex. Okay? So it cannot have this sort of straight part, okay, perfectly aligned with the budget. It cannot be like that. Okay, so it has to be all convex everywhere. Okay, like this or like this, right? Okay, so let's suppose this is x and this is x prime as we set in the argument. Okay, and again this would be the ux is u prime u star. Okay, and here if we have this, so we were talking about contradictions, right? So suppose that if we have two axes, x and x single prime, as the solution, Okay, then let's say some convex combination is somewhere here, x double prime. Okay, which is strictly better than that. But that is also feasible. Okay, so this violates the assumption that x and x double prime they're optimal, right? Okay, so then we conclude that there can be at most one element in the set X. Okay, and if we simply shift this blue curve, this indifferent set upwards, then this would be just the solution to that, right? And that would be the positive example, or the correct version of this statement, right? Okay, good. So up to here, then we have finished some properties of the solution set X given P and W for the utility maximization problem, right? So the first would be the first was the homogeneity of degree 0 in X, right? In P and W for X, and the second would be the binding constraint for this budget, and the third one the convexity for this X. Okay, and we could notice that in all those arguments or the proofs that we used today, we largely rely on the assumptions or the properties that we did before in the preference relations, right? So, and again, it verifies that those assumptions are very useful in the preference relations, so that we could derive these nice properties in the utility maximization problems in order to solve more problems. Okay, good.